In this video, we will talk about general change of variables in double integrals. Now, to understand what this tells us, okay, we already have some insight from polars. Using polar coordinates in a double integral is, of course, a very special change of variable. Now, let us recall how we change variables in a definite integral in the first place. Okay, let us consider, say, 2 to 3, something like sine x dx. Okay, I'm not going to evaluate this. One can, of course, but I will make a change of variable. I will let x be u squared. Now, how do we do that? Well, you all remember that we have this, and so we have sine of x is u squared, so u squared, and instead of dx, we have 2u du. And of course, these are endpoints, or the upper and lower values for x, which is u squared, so u starts from root 2 up to root 3. These are the u values. So this is now our change of variables. Now, what did we do actually here? Firstly, okay, we didn't have an extra term like this before. It came from the change of variable. Okay, we did not just replace x with u. We have a 2u factor. So this is a new factor. Secondly, okay, the interval changed. So there are two changes when we perform a change of variable. So, okay, firstly, a new factor. Okay, here 2u comes. And secondly, the domain of integration okay, here interval okay, changed from 2, 3 to root 2, root 3. So when we make a change of variable in a definite integral, two things happen. We get an extra factor coming from nowhere, and we change the interval. Okay. Now, how would this happen in a double integral? Well, exactly the same way. We will have an extra factor, and the domain of integration, well, here an interval, but in a double integral it's d, it will change. Now, how did it change? These are x values. Okay, so this is the interval depending on x. This is the interval for x. Now, these are u values. So, it is I sub u. In other words, interval for u. Now, we expect the same thing happens here. Okay. Again, let me just note that using polars in a double integral is a change of variable. Where, okay, the factor is r, okay, r comes from nowhere. It's not nowhere, of course, but it comes. And, okay, the domain in the xy system is changed to dr theta. The domain in the r theta system. Okay, we of course know this. For example, in Cartesian system, we have a wedge, a very strange domain. But when we use polars, actually we get a rectangle here. So it's changed as well. Now, so there are two changes in a change of variable. Now, how can we perform this in general? Okay. Say we change, okay, xy system to uv system. This means that there is a function connecting them. So with x is h of uv and y is g of uv. Of course, in one variable, x's f of u is enough, but in two variables, you may have two different functions. Well, of course, in polars, this is h of r theta, which is r times cosine theta. And here g is r times sine theta. So in polars, okay, h of r theta is r cosine theta, and g of r theta is r sine theta. Okay. Now, again, in reference to polars, in polars, we divided, okay, dxy, okay, which was, of course, some region in the xy system, okay, into small pieces. What kind of pieces? These were pieces like this. These were circles, these were rays, and we called this sum Sij. It's not a rectangle anymore, okay? But we divided our dxy, this whole region, into smaller regions like this. Okay, why was that? Because these were certain curves. These were the following curves. Here r was constant, some ri. The second one was another constant. It was ri plus some delta r. If you want, the difference is, okay, delta r type of thing. On the other hand, okay, this ray was theta is theta j, and this one was theta is theta j plus delta theta. I'm not using strict enumeration here, but the idea was increasing r from a constant to, okay, something where we add delta r to it, another constant, and theta again changed between two constants with the addition of some delta theta. So to use polars, we needed such a piece, and this piece, of course, corresponded to a rectangle in the r theta system. This simply means, okay, two r's and two thetas, where this was delta theta and this was delta r, so this is our Sij. theta is this, of course. So theta increases by delta theta, starting from some theta j, and the other one, starting from some Ri, increases by delta r. So if we change this little piece into Cartesian, this is something what we get. And as you remember, we calculated the area of Sij. That was what we did when we discussed polars. So let us now do the same thing. In other words, let us construct these four curves. Okay. What are these four curves? Well, this curve was R is constant. So here, U is constant. Okay. V is constant. And what are the other two? Okay. U is U0 plus delta U, and V is V0 plus delta V. Now here, okay, all four are constants. Okay, now let us try to sketch them in the Cartesian system, as we did in polars. Okay, in polars, when we sketched R is constant, theta is constant curves, we obtained circles or straight lines, and that's how we performed the partition of D. Let us do the same thing here. This is a little bit tricky. First of all, we said that, as in the previous case, if U is U0, we said we get a curve in Cartesian system. Well, is that really so? Okay, let me explain that. Say U is U0. Then, okay, xy becomes h of, okay, now U is constant, the other one is not, g of U0 V. Okay, so this is what happens to the point xy. U is constant, V is arbitrary. Okay, depending on, of course, the point. Now, if U is constant, then this looks like, okay, a function depending on one variable here and one variable here. Okay, you can think of V here as t, so it looks like a function of t, another function of t. Well, this is, as we know, a curve in plane. Okay, so this is, okay, this is like, okay, xy equal to x of v. Well, let me not use x, some other function. Well, maybe this, x of v, y of v. So it is a curve in xy system. Okay. And so on. So if we fix one of u or v, the other one is arbitrary, okay, we get a curve. Okay. Now, let us sketch this in detail. In the xy system. Well, u is u0 is a curve, as we saw here. Okay, so let me show it by which one? Right here, for instance. Okay, say this is the curve. U is u0 curve. We said it's a curve, so this is so. Well, if I say u is u0 plus delta u, again u is constant, but a different constant, so we get a different curve. Similarly, if v is constant, we get such curves. Okay. So these four curves can be characterized by u of v, a constant. Let me call this point A. This is in the xy system still. Okay, I showed this by B and this by C. That's all I need. Now here, okay, what is our goal? Our goal is to divide our D, which is a region in xy plane, into small pieces like this. Well, I sketched it very large, but actually it's very small because delta U and delta V are very small, and we assume all the functions are nice functions. That's H and G are nice functions, so they are continuous and so on. I will not go into that detail. Okay, this is an explanation, by the way. So let us write down what the point A is. Well, A is the intersection of V is V0 and U is U0. So it is a point xy well, let me use it this way. Okay, and this is actually, okay, because x was h function, and the other one was g function. So the point A is this. Now, what is the point B? Well, I will directly use H and G. Well, B is in the intersection of U is U0 plus delta U, and V is constant. So this is H of U0 plus delta U, V0, and G of U0 plus delta U, V0. Okay. And finally, the point C in question is the intersection of which U is U0 and V is V0, etc. So it is U0 and V0 plus delta V, and G of U0, V0 plus delta V. Okay, so these are the 3 points in question. Now, as you remember, even in polars, to calculate the area of R is constant and V is constant curve, which was something like this, if you remember. Okay, we had two things here and two curves. We wanted to calculate the area of this, and we approximated it because these were circles, straight lines, angles, and we could do that. Well, here it's not that easy because we have no idea what these curves at the top are. But we can do the following. Okay. Now, to estimate the area, okay, of the region bounded by the four curves in the figure, okay, we can use the following. First of all, A, B, C points and the fourth point, which I will not use, are very near each other. Okay. Because they are very near each other, okay, after all, in the integral, delta U and delta V will go to 0. So, if they are very small, then I can estimate the sides by straight lines. And the area will be the determinant of the cross product. So to estimate the area of in the figure, okay, we can use, okay, the area of, let me say, Sij I will show this by Sij. Okay. To estimate this, I will construct the vector AC, okay, and the vector AB. Okay. And that cross product will give, okay, the area of the parallelogram, which is more or less the same as the area of Sij. So, going back in this figure, okay, this is approximately the area of the parallelogram determined by well, AC cross AB. So, the area of Sij will be very near the length of the vector AC cross AB. From our discussions of vectors. Now, let us write down what these things are. Namely, okay, this is actually the determinant of I, J, K maybe I should do some economy here. Let me calculate this as follows. So, AC being C minus A, okay, from the left side, it is HO U0 V0 plus delta V. Okay, let me do the operation. Subtract the first component of A from here, minus HO U0 V0. Okay, and the second components of C and A would be U0 V0 plus delta V minus GO U0 V0. This is exactly what C minus A is. Well, I can write it as follows. This is HO U0 plus, U0 V0 plus delta V minus HO U0 V0. Let me divide this by delta V. I'm dividing the whole vector. Okay, this is a vector, of course, by delta V, and then I will multiply by delta V. This would be GO U0 V0 plus delta V minus GO U0 minus GO U0 V0 divided by delta V times delta V. Now, when delta V is very small, this ratio is almost, okay, the derivative of H with respect to V at U0, V0. So this is H sub the second one, H sub V at U0, V0. Approximately, okay. The first component is constant, only the second change, so it's H2, derivative of H with respect to the second variable, which is V in our case. And, okay, this one, by similar argument, would be G with respect to, again, V, O, U0, V0, times delta V. So this is the vector if we approximate it using derivatives. Now, similarly, AB, okay, This would be b minus a. And let me calculate that. This would be h of, this time, the first variable changed, so u plus b minus a. So yes, that would be u plus u0 plus delta u, and v0, okay, minus h of, again, a. So that would be u0, v0, okay. And the second component would be, this is the first difference. The second component would be the g's, u0 plus delta u, v0, minus g of u0, v0, okay? So that would be it. Now, again, as before, let me divide by delta u and multiply by delta. So this is approximately, okay, h. Now, the first variable is increased, and so this is the derivative of h with respect to u at the point u0, v0. I will not write this all the time. And the second one is similarly g sub u, u0, v0, times delta u. Okay. So now, using this simplified version, let me calculate area of Sij as the determinant of a, I calculated AC first, yes. So AC cross AB. Okay. This would be the determinant of, okay, I, J, K. Okay. Well, I'm taking the determinant of vectors of 2 entries, so the third ones will be zeros. The first one, AC, okay, over there, would be, roughly speaking, well, that's here, by the way, H sub B, G sub V, and H sub, the other one, H sub U, G sub U, which, okay, would be HB, GU, minus GB, HU. Okay. Now, this, of course, is the determinant. So this is the vector in question. Okay. So this is K. The others, the I and J components are zeros. Okay. Because if you take cross product of 2 vectors in plane, of course, it will be perpendicular to both. So it will only have K component. The others are zeros. But we take the length of it. Okay. The length certainly is the length of this vector. Okay. Which is the length of K being 1, which is just this absolute value. I can write it, of course, as follows. Absolute value, well, H was X after all. So X sub B, okay, G was Y sub U, minus XU, Y, V. Okay. In absolute value. Now, a shorter way of looking at it is that it's the determinant in absolute value of, okay, XU, XV, YU, YV. Okay. Well, actually, I changed the order, but it doesn't matter. I take the absolute value. Remember, in a determinant, if you change 2 rows, you multiply it by -1, but this absolute value takes care of that. And so this is this determinant. It is usually shown by del xy divided by del uv. It exactly means this determinant, but we take the absolute value. Okay. So this inside part is shown by del xy by del uv. Okay. And of course, I certainly forgot something. That is, in AB, I have a delta u here, and in the other one, I have a delta v. So actually, I multiply this with delta u, delta v. Okay. So I multiply this with delta u, delta v. So I have here delta u, delta v, and so on. So this is delta u, delta v here. Now, what does all this amount to? Well, it means the following. So, if we have here our dxy in the xy system, if I divide this into small pieces like this, where, okay, v is constant, etc., and v is v0 plus delta v. I will not write all of them. This is u0, and so on. So if I call this Sij, okay, then integral over dxy of fxy dA, I'm writing these indices just to indicate that we are in the xy system. This is a standard double integral. Okay. Now, that is the limit over i's and j's of f pij stars times area of sij's, because I changed this by, okay, I divided this into small sij's, a lot of them. I'm just taking one of them here as an example. So, and this point is a point in Sij. Okay. So I get this limit. That's my double integral by definition. Okay. Now what do I have? I know that this area is almost the same as this del xy divided by del uv, delta u, delta v, but with absolute value. Okay. So this is, okay, the limit of i's and j's of f of pij star, where this is chosen from Sij, times del xy by del uv. Okay. Now, delta u, delta v is the area of the rectangle with sides delta u and delta v in the uv system. So it is actually, let me write it, I will just comment later. Now, when we look at this limit of double sums, we see that thinking this as a function of a new function of u and v. I changed everything into uv's here. I can do that. Times the area in the uv system of a small rectangle. But by the very definition, this is the double integral of f times del xy by del uv dA uv. And of course, uv change in the new system. In f, of course, I will put uv's. Okay. So our change of variable is completed. Okay. So what happens now? This absolute value of this determinant, okay, which can be very simply written as, okay, the determinant of the matrix where x's and y's are differentiated with respect to u's and v's. So this is the determinant of the first, I should say this as, I didn't use that notation, so okay, forget this. One can easily say it to remember it, but this is nothing but absolute value of the determinant of xu, y, xv, yu, yv. Okay. It's called the Jacobian determinant. Okay. Without determinant, it's just called the Jacobian. Okay. Note that the Jacobian here plays the role of the derivative of the function when you make a change of variable. Something like if x is g of u, then the derivative of g is here. It's a derivative of x with respect to u. So it's dx du in one variable. Here it's the Jacobian determinant. Okay. So this is what change of variable in two variables is about. Now, let us have some remarks. So far are some theoretical, or rather practical, remarks to understand things better. Now, in one variable, let me say in R, okay, the factor in a change of variable is nothing but dx by du. Okay, x is a function of u, and this is what you get as the extra factor as we considered at the very beginning of our discussion. Now in R2, this factor becomes del xy by del uv, but in absolute value. Okay. Now this is important because in the first case, in one variable, we don't get absolute value. But the geometric meaning is more or less there. That's to say, what is dx by du? Okay. Now dx by du, okay, so geometrically this means the following. Dx by du in one variable is something like del x by del u, which can be considered as a difference in x's divided by a difference in u's. But the substitution that we used was, say, g of u. Okay? This means that g of u2 minus g of u1 over u2 minus u1. In other words, okay, these are the difference in the two values in the u real line. Okay, and these are the corresponding thing in x real line. So this is a ratio of lengths, namely in the u-axis, okay, the length is u2 minus u1, and this becomes, after the change of variable in the x-axis, okay, it becomes g of u2 and u1 and g of u2. So it becomes this. And these lengths are not equal, clearly, because these are for the x values, these are for the u values. Remember our example, x changed from 2 to 3, but u was the square function, and so u changed from root 2 up to root 3. So the length shrank to a new thing. So this is the ratio of lengths, but on a differential level. That is, when these two are getting nearer and nearer. Only then this factor tells us that it's the ratio of lengths. Now, okay, in R2 case, what do we get? Del xy by del uv. Well, this was precisely, when we look at what we did over there, this is the ratio of areas, okay, to area of rectangle, okay, delta u, delta b. So this is then ratio of, okay, areas. Okay. Before and after the transformation, the substitution. Okay. Well, that's why we use absolute value here. But there are more subtle reasons for it, but I will not go into that. Well, as you can, of course, generalize from here, we did not consider them yet, but if you wanted to make a change of variable in 3 variables, a 3-variable integral, they are called triple integrals, okay, this would be a ratio of volumes, and so on. So this is the geometric meaning over there. Well, a second thing. So let this be the first remark. A second remark. Okay. For the transformation, x is r cosine theta, and r sine theta, y is r sine theta. That's in polar transformation. Let us see what this del xy by del r theta becomes. Okay. Remember, it was the determinant of, okay, x with respect to first and then the second variable, y with respect to the first and the second variable. And this determinant would be determinant of, well, derivative of x with respect to r would be cosine theta. Okay, with respect to theta would be minus r sine theta. And y, that is r sine theta, this would be sine theta, and this would be r cosine theta, which is, of course, r cosine square minus minus r sine square, so it's just r. Okay. Well, normally we put absolute value, but when you put absolute value, r being positive, you still get r. So that's why we have an extra r in polar substitutions. That's exactly the ratio of areas, the differential ratio, of course, namely, when deltas are very small, it's approximately r times. So it increases the areas by r, the polar transformation. Okay. Well, let us see how we can use this to our advantage. Let us see some examples. Okay, evaluate I, which is the double integral of dA over x squared, x plus y. Okay, where D is the following region in the xy system. It goes as two lines and another two lines here. These are x plus y is 1. This is x plus y is 2. And this is y is 2x. And this is y is 4x. And this is the region. Okay. Note that this is indeed a region in the first quadrant, so everything is positive, we can divide, etc. X is not 0, x plus y is not 0, and so on. Secondly, okay, if you wanted to evaluate this integral directly, that means dividing d is not simple with respect to x or y. So if you divide d into parts where you get simple regions with respect to x first or y first, you will get 3 of them. You can check that. And evaluating this 3 times over such strange calculations would take you a whole page of calculation. But it's possible, of course. So direct evaluation is possible, but not very wise. Using Cartesian coordinates, is possible, but not practical. Okay, so what do we want to do? Well, we concentrate on D. Of course, it means the curves bounding D, because when we transform these 4 curves, it means the inside part will be the inside part, and so it will be transferred into the new variable system. So what is our new variable system? So what is almost constant or very simple in this formulation? Well, clearly, this line is x plus y is 1 or x plus y is 2. Well, that means x plus y changes from a constant to another constant. Similarly here, y over x changed from 2 to 4. Now, this hint tells us that let u, for example, be y over x and v be x plus 1. Then, okay, u changed from, that is y over x, changed from 2 to 4, and v, that's x plus y, changed from 1 to 2. In other words, this transformation changed this strange-looking piece D into a nice rectangle, because they change between constants. Well, with this transformation, of course, to make the transformation, we need to calculate del xy by del uv. However, we do not know xy as functions of u and v. Actually, we can find it. So here, okay, in other words, to calculate this, okay, we either find, okay, x and y as functions of uv, and then carry out the operation, okay, or, okay, use, okay, the property of determinants, or rather Jacobians, which is very important here, or use the following fact from linear algebra. The determinant of xy with respect to uv is the same as 1 over the determinant of uv with respect to xy. Okay. Well, we will not prove it. Okay. It can be proven using the chain rule, though. It's not that difficult. But you need a lot of extra conditions, namely all these functions must be nice, and so on. Okay. Fact of or about Jacobian determinants. It's very practical, so we will use it. Okay. Without proof. So now, as you can see, you can solve y and x from here, from these two equations, but it's not always very useful or simple, and it's not practical. So the second approach is much better. So let us calculate then, okay, del uv by del xy. Remember, this is the determinant of ux, uy, vx, vy. So it is the determinant of, okay, let us look at the top. U is y over x, so this is minus y over x squared. The other one is, with respect to y, 1 over x simply, and derivatives of v are 1s. Okay. So this is minus y over x squared minus 1 over x. Or if you want, multiply by x, it's minus x plus y divided by x squared. Okay. Now, so the integral over d of, these are in xy system yet, over x squared, x plus y, happens to be integral over duv of dA, let me, okay, write it one by one. Now x squared, x plus y, times, okay, the absolute value, but this is del uv by del xy. So it is 1 over minus x plus y divided by x squared in absolute value, okay, and then dA uv. Now, what does all this tell us? Of course, I wrote everything inside in terms of x's and y's, but the calculation part is done, so I can directly change them into u's and v's. Certainly, these cancel out, and in absolute value, that becomes x plus y, because x plus y is positive. So this becomes, okay, 1 over x plus y squared, which is v squared, okay, dAu. Now, okay, what is the region in the UV system? Now, to find this, we go back to the original region, which is, okay, clearly telling us that y over x changed from 2 to 4, but y over x is u. So u changed from 2 up to 4. And the other one, that is x plus y, changed from 1 to 2. So it becomes this rectangle. And so I can now write in iterated integrals 1 over v squared, okay, du dv. It's not important which order I use because it's a rectangle. U changed from 2 to 4, v 1 to 2. And this is very easy to calculate. I will not do that. If I'm correct, of course, that is to be 1. Very simply. So this change of variable changed the region into a rectangle. Has made the calculation very simple. Okay. However, note that when you make a change of variables in a double integral, you have to be careful about not one, but 2 things. Namely, okay, just making the function an easier one is not the concern only. In one variable, in definite integrals, we only looked at the function. Okay, made a change of variable, and the result was easier to integrate. The upper and lower bounds of the integral could be adjusted directly. Okay, instead of AB, you had something else, and you can see it from the transformation immediately, and it did not pose a problem. But here, duv can pose a problem. This can be a very strange region, and you don't want to integrate over that. Or you forget the function, you just change the region. You may want to make the region a more presentable one, a simpler one, so that you can directly evaluate your integral. So there are 2 things you have to take into consideration in a change of variable in double integrals. Okay. Well, let me continue with more examples. Well, as a second example, let us evaluate the integral e to the y minus x divided by y plus x dA. Everything is in xy coordinate system, and D is the region, this one, 1, 1, in the xy system. Now, the trouble here is that the region is very simple. There's no problem at all. Okay, it's simple with respect to x first or y first. But the function is very difficult. In other words, okay, either with respect to x or y, we do not know a nice antiderivative for this function. So here, okay, we cannot express an antiderivative of our function in terms of elementary functions that we know. Okay? With respect to x or y, so here, okay, it is impossible to calculate it directly, even though the region is very simple. So the problem wholly lies on, okay, the variables, the function. Well, one way, of course, to get around this is the following. Well, what's the difficulty here? The difficulty is that if we just had, okay, no x's, but just y's, or just x's, that will be very simple to evaluate. Okay. Or basically, if at the bottom, okay, we didn't have these variables, but a constant, it would be simple. So let us reduce these expressions, y minus x and y plus x, to something, okay, new where there are no extra constants. So let, for example, u is y minus x, v is y plus x. Then it is e to the u over v, no constants. And we can integrate with respect to u first, not v. Okay, let us try that. Of course, when we do this, certainly we need the Jacobian determinant. In other words, we need the derivative of, okay, xy, that is the Jacobian determinant, with respect to uv. Well, here, as I said before, you can directly calculate x or y very easily, so we can do that, or use the reciprocal of the determinant of the Jacobian. For example, adding, you get y, u plus v over 2. And x, well, for that you have to subtract v minus u over 2. Okay. So you can directly calculate the determinant of x with respect to u and v, minus 1/2 and 1/2, y with respect to u and v, 1/2 and 1/2, and that determinant is minus 1 over 4, minus 1 over 4, so it's minus 1 over 2. Okay. Or find 1 over del uv by del xy, as we did before. Here it's not necessary, but you can do that, of course. So then, the second thing is to find duv. So to find duv, that is, what happens to this triangle in the uv system? Well, for that, we transform the curves that bound it. So what are these curves? Well, x is 0, y is 0, and x plus y is 1. Now, what does x equal to 0 become? Well, let us look at the transformation. If x is 0, it means that u is y and v is y, so they're equal. So this says v is u. If y is 0, clearly u and v are opposites of each other. In other words, v is minus u. And if x plus y is 1, okay, well, x plus y is v, so v is 1. So this tells us that in the uv system, it doesn't matter whether you put u or v, as long as you are consistent. Okay, it tells us that v is u, okay, v is minus u, and v is 1. So this is our duv. Now going back to the integral, okay, let us form our integral now. dxy e to the x minus y minus x and y plus x dA. That becomes duv, okay, e to the u is y minus x, u over v, okay, times the Jacobian determinant, which is minus 1 over 2. Okay, but remember, absolute value. It's from the theorem. Times dA uv. Now, duv is a nice triangle, which is actually simple if you take u first. Okay. And do we want to take u first? Well, yes, because we cannot integrate this with respect to v. E to the 1 over v does not have a nice antiderivative. So, okay, let us evaluate this with respect to u first. So we look in the u direction in that triangle, So u changed from minus v up to v. And in the meantime, v changed from 0 to 1. This, of course, tells us that we have 1/2 integral 0 to 1. Now, if you put u equal to v, you get e. If you put u equal to minus v, you get minus 1 ev, which, of course, is e minus 1 over e divided by v. In a very nice, simple way. Well, of course, here, many things fit together so that there were simplifications. There was using b first, which simplified the exponential just to constants, and everything was nice after that. As a third example, let us consider the following rather two-dimensional looking problem. Let us find the area bounded by, the area of the region and B bounded by the following four curves. Okay, x squared is a times y, x squared is b times y, and y squared is c times x, and y squared is d times x. Now these are constant here, it's not dx, where of course these are all positive numbers. B is the larger one and c is the smaller one. So this is the region bounded by these four curves. Let us sketch it first and see what it looks like. In the first place, x squared is ay or x squared is by are parabolas, but the other way around. That's to say, these are parabolas of the following sort. Okay. Well, when you look at this, you can figure out which is A and which is B case. Clearly, if B is larger, it means that X will be larger. So this is the B case. And this is the A case. Okay. For the same Y, okay, in the first case, X is larger. Wait a minute. I just wrote the opposite. Okay, the argument is the following. For the same Y level, okay, the B is larger, so this is the bigger one. So this is more to the right, so it's correct. So for the same Y level, okay, this B version is larger, X, so it's correct. And you have two, wait a minute, it's just the opposite. Well, these are the Y's, of course. So this is Y, this is CX, this is Y, and this is dx. And again, here, for the same Y squared, D1 would be larger, so this is it. And the others, the first two, are standard parabolas. They're like this. Okay. And y is x squared over a, x squared over b. B is the larger one. Okay. So y is smaller here for the same x. In other words, this is x squared is by, and this is x squared is ay. Okay, and the region in question is this part. It's bounded by these four parabolas, okay, all four of them. A hint actually, when your curves determine a lot of bounded regions, for example, here you have 1, 2, 3, 4, a lot of regions, okay? What is meant is the one which uses all of them. So, this is a bounded region, but it uses only 3 of these curves, not the 4th one. Okay, but this one uses all 4 of them, so it is the one that is meant. Usually it will be more explicitly stated, but if not, this is what you should understand from it. Okay. Well, what do we do in this case? We want to find the area. So, okay, let me give a name to it. This is dxy, because this is the xy system. Clearly, the area wanted is the integral over dxy of 1 dx. That's the standard area concept in double integrals. The problem is d is very complicated. Actually, it's not simple with respect to x or y. It doesn't look like polar or anything, standard. Okay. So, okay, either we divide it into 3 pieces and calculate these integrals, which will be quite complicated, or make use of some change of variance. Now we observe that in the boundaries of dxy, okay, some things change between constants. For example, x squared is ay, x squared is by. Which means that x squared over y changes from a to b. Okay. And similarly, for the other one, namely y squared over x, this changes from c to d. Okay. Actually, these arrows don't mean much. What I mean is x squared over y is equal to a or equal to b, but because b is larger, that's I showed it this way. Well, so let u be x squared over y, v be y squared over x. Then this transformation will change that strange region into a rectangle, a to b and c to d. Okay, we need the Jacobian determinant. I don't want to solve for x's or y's, simply calculate del uv by del xy. This was the determinant of ux, uy, vx, vy. This is the determinant of, now u sub x is 2x over y, okay, u sub y, okay, would be minus x squared over y squared, and the derivatives of v with respect to x would be minus y squared over x squared, and 2y over x. Now the determinant is this product minus this product, which of course says that you have 4, just 4, minus, again, just 1, so it is 3. Okay. So, it says then that we should multiply okay, our function in the integral by 1 over 3, because we want del xy by del uv. So then, okay, the second thing is to determine DUV. What happens to our region? Well, as I said, and which is clear from the conditions, it is just in the UV system. As I said here, okay, this was my U. U changed from A to B, and this changed from C to D. So it's a very nice region. Well, it means that, so area would be, okay, 1 times, okay, the absolute value of this determinant, but 1 over that. So it is 1 over del UV, del XY, in absolute value, which of course happens to be 1 over 3. Okay? And du dv, because I have no u's and v's inside, actually it doesn't matter. And uv, u changed from A to B, and the other one, C to B, because this is a rectangle. Well, all in all, it tells me that I have 1/3 of d minus A times d minus. So it simplified the calculation quite a lot by changing this region into a rectangle. Okay. Well, a last example. That's my fourth example. Okay, we want to evaluate the integral over d of 1 minus x squared over 4 y squared over 9 to the power 8 dx. This is in Cartesian, of course, and dxy is the region which is the xy's such that x squared over 4, y squared over 9 is less than or equal to 1. So it is the inside of the ellipse. It's not necessary to sketch this at this point, but let me just sketch it. Okay, if you, okay, sketch the equality case. When x is 2, y will be 0. When y is 3, x will be 0. So it is something like this. It's an ellipse with this property. Okay. Now, if we didn't have these 4s and 9s, it would say that we would have a circle, and this would be 1 minus x squared minus y squared. Well, it's a perfect setting for polars. So we could use polars directly. It will simplify a lot, and so on and so on. But we have them. So what do we do? Well, polars tell us, namely, let me say that, if, okay, the ellipse were a circle, okay, that is, okay, we didn't have 4, 9, okay, then we could use polars. Okay. But we have an ellipse, and we want to use polars. What's the advantage of the polars? The advantage is that this ellipse, or the circle, becomes r equal to a constant. And that's a very good simplification. Let us try to do that. So, normally, we would have x is r cosine theta, and y is r sine theta in polars. But if we put them in here, well, this ellipse is quite strange. Okay, it is okay, not just r, it is r squared cosine squared divided by 4 and divided by 9. All this complicates the matter. We cannot use sine squared plus cosine squared is 1. To use that, when we put them in place here, okay, we should have just x squared plus y squared, namely r squared. To guarantee that, obviously, you have to multiply your x by 2, so that when you square it, 4's cancel. Put a 3 in front of y, so 9's cancel. You just have the sum of the squares. So, okay, multiply this by 2, multiply this by 3. So use modified polars. Okay. Now what again is the advantage? Then, okay, clearly x squared over 4 plus y squared over 9 becomes, take the squares, 2's and 3's cancel with 4 and 9, you get r directly. Actually, yes, this is what you get. And here the boundary is, this is equal to 1. So this ellipse becomes a circle. Becomes the circle r equal to 1. Now this is a big advantage, of course. It makes the calculation a lot easier. Well, all you have to do is calculate the Jacobian determinant. I'm using r and theta, but they are not the polar r and theta. You should be careful about that. Maybe I should put r prime and theta prime. I will not do that. Okay, but they are different than usual polars. Okay, because of 2 and 3, the scaling is changed, and it changed an ellipse into a circle. Okay. So we have to calculate the determinant. It's not the same as the polar determinant, of course. This would be the determinant of, let me calculate it directly, derivative of x with respect to r and theta, so 2 cosine theta, and with respect to theta, minus 2r sine theta, and y with respect to r would be 3 sine theta, and this one would be 3r cosine theta, and this determinant would be 6r cosine squared minus minus plus 6r sine squared, so it would be 6r. So by introducing 2 and 3, because we take the derivatives, okay, the product comes into the picture. Well, this is what we want. Okay, so the integral becomes the integral over duv of, well, here we have 1 minus the sum of these two squares, which is exactly from this calculation equal to r. So it's nothing but 1 minus r squared to the power 8 times the Jacobian. Well, we need absolute value, but it's the same as 6r, okay? dA r theta. UVs are r theta. Okay. Now, well, what is the r theta? Clearly, in the r theta system, okay, what happens to our d in the original? D was the inside of this ellipse, but this ellipse is r equal to 1. We calculated that. It's a circle now with this new variable. So it becomes 0 to 1 and 0 to 2. It's actually a circle in dr theta. So this becomes 1 minus r squared to the 8th power 6r dr d theta r 0 to 1 theta 0 to 2 pi, which is very simple to evaluate. You have 1 minus r squared to the 9 over 9 times minus 2, and you have a 6 here, and then r changed from 0 to 1, and you multiply it eventually with 2 pi, so it becomes, 1 over 3, right? At 1 you have 0, so you have the plus version, so it's just 1 over 3 times 2. So it simplifies the calculation quite a lot.